everyone. We're going to be attempting question 16. Now, which activity has the longest float time? So, the longest float time is denoted by, it's easy to calculate if you have a backward scan. So I calculated, I'll just give you a sample of one of them that I calculated, and I suppose all of you will know that if it's not on the critical path, it'll have a float time, the activity. And so what I first did was determine what was the critical path. So 0 plus 5 is 5. 5 plus 7 is 12. 12 plus 3 is 15. 15 plus 4 is 19. 19 plus 5 is 24. And 24 plus 2 is 26. I find that's the easiest way to actually calculate the critical path. Now, so in order to answer the question about the biggest float time, I did a calculation of float time, and I found that E was the one that gave me the greatest float time. Now, if you had a backward scan value, 10, it's easy to see that the latest E can start is after 10 days, but the earliest it can start is after 5 days. And therefore, 10 take away 5 is a float time of 5 days. Otherwise, we do the latest at the end of the edge minus the earliest in the beginning of the edge minus duration time. So 15 take away 5 is 5 days. And that is the activity with the longest float time, which I have also indicated over here. The management of the theme park decides that the tilt-a-whirl attraction will be closed for too long to complete the project. They give the project manager a budget to reduce the overall completion time. So these are the activities that can, and the costs they incur in order to reduce the completion time. So here they've given you a reduction in completion time of 0, 1, or 2 days. And we have been asked to fill up the box, and these are the costs involved in this reduction. I have 3 different methods which I usually move between, and you can choose as to which one you find the most convenient. The first method is to put down all the paths that constitute the network and the original length along those paths. So is the length along the duration time along A plus C plus I plus J plus L gives me 23. I also highlight all the activities that can be reduced along all those paths, which are A, B, D, E, G, H. Now, once I calculate the original path duration, I find that 26 is the critical path, which is the largest value. Now, having highlighted all these reducible activities, and the maximum reduction that possibly exists that I can possibly do is 2 days, I subtract from the original path the duration that can be reduced. So A is 2, and therefore 23 take away 2 is 21. And here in the second path, it's 4, 2 plus 2. And there A and H, and so 21 take away 4 is 17. In the third path, it's A and G, so 25 take away 4 is 21. In the fourth path, it's B and D, and 24 take away 4 is 20. In the fifth path, there is B, D, and H, and that is totally 6. So 22 take away 6 is 16. And BDF, GKL is 1, 2, and 3 activities. That's a total of 6, which constitutes to 20. And then 21 take away 6, and the last one is Sorry, 21 take away is 6 would be 15 here. Okay. And then I start looking at keeping in mind what can be reduced and which reduction would help me cover the maximum number of paths, keeping the cost in mind too. So I start with the critical path and I find an activity on the critical path, let's say G, which I can reduce. And so I go down maximum reduction of G, and because it's 2, 26 reduces to 24, and every other path which has a G in it also reduces by 1, giving me 23, 21, 23, 24, 22, 24, and 19. Now we have 2 critical paths of 24. Now, the maximum reduction column actually helps you because when you did the maximum reduction, you got a maximum value of 21. This gives you an indication as to when you should stop crashing. So when you reach 21 and your critical path becomes 21, that's when you stop. And then we look again at the 2 critical paths, 23, 23 here. And 24, 24 here, sorry. And we find that we have a path B in common. So we reduce B by 2 days, and so all these stay the same, but those with B reduce by 2, reduce by 2, reduce by 2, and reduce by 2. And now our new critical paths have a completion time of 23, 23. And we try and see what's common between the two, and we find A common, and we reduce A by 2. And so all the paths with A reduce by 2, giving us this column. Now we have these two as our critical paths because they have the maximum value. And we have already reduced B by 2 along those paths. So we have to find something new, and we know that the maximum reduction we can go down to is 21. So reducing by 2 is really a waste of money, and therefore we have to find one activity common between these two that takes us down to 21, and that is D. So in all these paths, D don't exist, this one and this one too, this one it does, so that goes down to 21, and this one does too, it really doesn't matter, but it goes down to 19, and this one takes us down to 21, and that stays the same, 17. Now we've reached our original critical path has been crashed and gives us the maximum reduction of 21. The other method that you could do is what we call the required to do method. In this method, we compare the old path to the new critical path value, which is 21. So the old path originally was 23 for this particular path. So 23 is greater than 21 by 2. And the only activity that can be crashed over there is A, and therefore we reduce A by 2. On the second path, 21 is equal to 21. When they're equal, you do nothing. The only time you crash is when the original path is greater than the maximum reduction possible. Now, on the third path, 25 is greater than 21. And on that path, we have A and G. Now, if we have previously crashed A in a previous path, we should crash it again on any path after that by the same value if possible. So 25 is greater than 21 by 4. And so we start by crashing A by 2 because we've crashed it before. And the other activity that we can crash is G. And so we crash G by 2. And 2 plus 2 constitutes 4. In the next path, 24 is greater than 21 by 3. In this path, we have B and D. Now B is cheaper than D, and therefore we'll crash B by 2 and D by 1. In the next path, 22 is greater than 21 by 1, and the only activity over there is that we could crash by 1 because we previously crashed D by 1 is D. So we should try and keep them as common as possible. On this path, 26 is greater than 21 by 5, and we can crash B, D, and G. So we crash B by 2 because we've crashed B before, G by 2 because we've crashed G before, and D by 1, which keeps it common with a previously crashed path. The last one, 21, is equal to 21, and we do nothing. So if we combine all these different crashings together, A crashes by 2, B crashes by 2, G crashes by 2, and D crashes by 1. And those are the values that we have recorded here. So this maximum reduction column gives us a good idea as to when we should stop crashing, because often students have that problem. So you could either choose the first method, which is crashing along single paths. You can either crash them by 2 as I have, or you can do crash 1 at a time and stop when you reach that final 21. Or you can adopt this required to do method and then crash and then record all of the crashings that are possible. Now, I find the analytical method of looking at it actually much easier. So this is the original diagram. And if we need to crash activities, what we're basically trying to do is reduce the minimum completion time, which is determined by the forward scan. So what I have done is actually broken up, and I have also recorded the costs involved, because that will help us decide which activities can be crashed more than others. So now I've broken up this network into, so these are the places where you make choices. So that's here, that's here, that's here, and here as well. And that determines your minimum completion time. Now, what I do is I usually highlight the activities on the diagram that can be crashed. And then I think of the maximum crashing possible and how it would affect the choices. So if I went along the path AC in order to come to the first choice, and I did the maximum crashing of A by 2, I would get the duration for activity A is 3 days. So that takes me from 0 to 3 over here as the earliest starting time for activity C. And then 3 plus 6, 9 is the choice here. Now, if I hadn't crashed B and D and I had just gone along 0 plus 5, I would have got a 5 here. And 5 plus 7, I would have got a 12 there. Now, that tells me that the maximum I can crash B and D down to, the value 12 down to is 9, because I can't crash below 9 as I have done the maximum crashing on A. And so I have to decide. So 12 take away 9 is 3. That means one of these activities goes down by 2 and the other goes down by 1. Now this is where costs come into play. So if activity B is cheaper than activity D, you will crash B by 2 and bring that down to 3 days, and activity D by 1 and bring that down to 7. So 0 plus the duration of B gives you the earliest starting time of activity D, which is 3, and 3 plus 6 gives you 9 over here. Therefore, you have actually reduced the choice. Originally it was 12, you've reduced it to 9 over here. So that's your first step. And then you look at it and say, okay, fine, I can't crash activity F. So I have to 9 plus the duration time for F, which is 3, 12 is the minimum I can bring that path down to. Now I can crash activity E, but if I add the original earliest starting time plus duration time, it gives me 8, which is already less than 12. So it's no use crashing E further because it's not going to affect 12. The choice that you make will still be the larger value, which will be 12. So don't bother crashing E. And now the next choice is at this point here. So 9, I know I can crash H. I can also crash G. So I started by crashing G by 2, and 12 plus 2 took me to 14 here. And I found that if I added 9, the duration time of activity H, 9 plus 3 got me down to 12, which was clearly less than the choice 14 on the other edge. And so it was no use crashing H because that would be a waste of money. I would still choose 12, which is the other edge. So I bring I would choose 14. 12 plus 2, which is 14. So the two choices are 12 on this edge, 14 on that edge. I would choose 14 as my earliest starting time for activity K, which is a larger value. Now, after this, there are no activities that can be crashed. So 14 plus 5 takes you to 19 here. And as you come along, 9 plus 4 is 13 here, and 13 plus 6 is 19. And that sort of makes me comfortable because both the choices are 19, and I know I can't reduce any further. And so I choose 19 at the end of K, which is here, and 19 plus 19 here instead of 24, which was a choice I had made previously, and then 19 plus 2's minimum completion time is now 21. And so that is the third method. And I can clearly see over here, I have actually laid down the logic here from choice to choice. These are the 3 places I made choices, and I've explained clearly over here as to why I chose. And then when I record all the crashings that I did, it's A by 2, B by 2, D by 1, E by 0, H by 0, and G by 2. This method is a lot simpler than recording the parts and is more analytical and easier to think. So I hope I've helped you answer the last question in the NHT paper. And if you have any suggestions or comments, please do comment below. Thank you for watching. Bye-bye.